It's so great to see you again. This is the week close to midterm, and like a lot of people already feels like, okay, I don't want to go to campus anymore, and same thing as me. So and so that's why people are expecting like the day November the second coming from when we transition from the daylight saving time to the normal standard time, so we get an extra hour, so we don't have to wake up in the dark morning, right? Which is exactly where I came from this morning. So we played a song to you again because we are going to see the case study again. Last time we talked about matrix multiplications. We haven't finished it, and I know you have a lot of questions. So today we are going to revisit the matrix multiplication again, and let's talk more about matrix multiplication. But before we start, the big problem in matrix multiplication, as you can see the last time, is we have a lot of cache misses. And why cache misses is a problem? Because the memory and the processor has a huge gap in performance. So whenever you have a memory, you have a cache miss, it means that you are potentially going to visit the slow DRAM. And we want to, in computer architects, we built such a good facility called cache that only require very small amount of SRAMs, which are more expensive to be added into your processor, and hopefully that will capture most of the data that you need to avoid the chances that you are visiting the slow memory. And however, the key thing to optimize for application performance, as we mentioned, is to improve the performance of your code to avoid cache misses. So to avoid cache misses, you need to take some actions. And however, a lot of people, when we are doing engineering projects, we thought, oh, okay, here are the methods that I know. I try it ad hocly and one by one. Is that right? That's not the right approach, right? So the best thing that you have to do first is that identify the source. What's the cause of that problem, right? So that's why it's always so important for us to figure out where is the potential of the performance problem. So that's why in the very beginning, we introduced the performance equation so that you know I see CPI, which I should improve. And then we talk about m.slow so that you know which component should I improve. And now, if we know the problem is because of cache misses, how to improve the cache misses? So there are 3 different types of cache misses. For example, compulsory miss means the first time you ever access a block in these pieces of a code. That's called compulsory misses. And the second type of misses is called capacity miss. So first of all, if this miss is not because the first visit of a block, then it cannot be compulsory misses. It has to be the second or the third type of misses. For capacity misses, it's the case where the working size of your application is too large. And what does that mean by working set size? It means the last time, so right now you have a miss on this particular block, right? So before this miss occurs, and the last time you visit the same block, how many other blocks in between have you visited? That's your working set size. If that's more than the number of blocks that you can have in your cache, that's why you have capacity misses. However, there are also cases where even though your working set size is not larger than your cache, you still see a lot of misses. And one of the situations might occur here is conflict misses. Because many blocks, they map to the same set in your cache. However, we have limited set associativity within each set. So that's where the conflict miss is coming from. And that doesn't happen that does happen even though you have large enough cache. So that's the difference between these three types of misses. And depending on what type of misses you have, we have different treatments. So for example, if it's compulsory misses, then we should use prefetching to look at a block ahead of time and then place the block in a separate small buffer so that we can avoid the prefetch block to kick out the block that you really need. Or if it's a conflict miss, you can potentially use add victim cache to your processor so that whenever a block is evicted, I still have a shelter for it. That's the victim cache. However, both approaches that I mentioned would cause additional hardware cost, and this has to be done by the hardware perspective, and most of the time, we don't have access to the hardware design. So we introduced several important approaches to improve the code performance, even though you don't need hardware. So one of the things that we have to first thinking about is that is the data structure design aligned with the common access pattern that you will see in your code? If that's not the case, then you should revisit it. So sometimes we want column store, sometimes we want row store. It completely depending on what's the most frequently used pattern. So as you can imagine, for these pieces of a code, if you have a column store and you are mostly traversed by columns, then you can reduce the memory footprint that you need to visit. So it turns out you are going to improve capacity misses and potentially also compulsory misses because each block will contain the data. The utilization of data within each block will be a lot more, right? So you are having more condensed information within each block so that I only need to fetch fewer number of blocks, and the number of blocks that you fetch would actually impact your compulsory misses. And also, if you have a loop, am I structuring the loop in the right way? So we have different loop optimizations. So for example, loop interchange to change the traversal order of my loop. Or if I have limited weight associativity, I should try loop fission so that I don't need my cache to track so many data structures concurrently. Or I can do loop fusion if I have enough weight associativity so that within the same loop, I just visit all streams of data so that I can reduce the amount of memory accesses or avoid the capacity misses because if one of the data structure is too large and you have to revisit it, right? So you can check for the software optimizations that we have. Like if you can find the data layout, you can avoid all three types of misses. If you try to interchange your loop, you can potentially reduce the conflict or capacity misses. If you try to do loop fission, that's pretty much because of if you have a situation of conflict misses. But since conflict misses is because you don't have sufficient amount of weights. So if today you have a processor with a lot of weight associativity, then you probably don't want to do loop fission. Instead, you want to do loop fusion. So today we are going to continue talking about tiling and blocking algorithm. So the last time we talked about this is how matrix multiplication works in general. So whenever you want to calculate an entry within the matrix, what you have to do is that you take one row and a column. And if you look at the behavior of this, right? Whenever you want to visit a column, remember each column right now is occupying a block because each of this horizontal, 8 of them is a block, right? So it turns out for this, you need 2K blocks, right? And remember, for our Core i7 processor, we only have 768 blocks. So that's why it's a capacity misses. Because once you traverse a row, you are going to use out all your capacities. So that's not going to work out, right? So then, what we are thinking about is that, can we try to reduce the working set, or say the memory footprint that we visit between visits to the same block, right? So let's say the same block here is probably A, or the first element of B, right? So in the past, right, if I visit the same element in B, then it would take a few other rows. So definitely they are not going to be there, right? So how can I reduce the number of blocks that I have to visit before and after, right? So then the approach that we are thinking about is based on the mathematical observations that you can break up matrix multiplications in a lot of subset of multiplication and accumulations. And if you structure them correctly, for example, instead of going all the way to the end, I can try to do this. I can accumulate the value of C00 with several runs. However, for each run, instead of going through all the way to the end of a row or the column, I only go to a subset of it, right? So, for example, right now in this slide, I'm only using 8, right? So every time I'm only multiplying and accumulate 8. So the first time I only need to access 8 elements in a row and 8 elements in a column, right? So at this point, you can imagine, even though each element would occupy a separate block, but if I only access 8 of them, I'm only using 8 blocks, right? So that perfectly fits into my cache size. Remember, our cache has 768 blocks, right? So I only use 8 here. And for this row, I only have 8 elements, so they are just 1 block, right? And for this C, it's only 1 block for now, right? So total, I only use 10 blocks for now. Now, if I stop here and go back, instead of calculating the rest of C00, if I go to C01, then what I need is, again, this row and the next column. You might think, okay, a new column, right? But remember, this is our block boundary. So the next element to each column is actually already in your cache during the first compulsory misses, right? So this is going to be a hit, this is going to be a hit, and this is going to be a hit, right? So it means, well, if our boundary is 8 here, right? So you can safely assume if I just want to calculate at this boundary, I will be fine, right? So if you keep going, right, all the way to the end, you'll be fine. And at this point, you have everything in a tile of B has been visited. Now, what are the remaining tasks that we need to do for the rest of them? We can keep going on, right? So now, instead of going all the way through, right, can we calculate the next line, right? And then, although I fetch another row here, but for a short period of time, I'm not going to use the previous row anymore, right? Because that's how the way the algorithm itself it is. So then for this part, this 8 blocks, I keep reusing it, right? And I only have compulsory misses every time I meet a new row here and there, right? So you can imagine when I partition the tiles in A by A, what happened is that I would have A compulsory misses here, A compulsory misses here, and A compulsory misses here. So if you imagine that, whenever I compute on a tile, this is the total amount of memory access that I would pay. However, I only have this amount of misses. So the overall miss rate so far is only 1.5. It's not just that. So let's keep going. So right now, if I am here, I want to calculate the next row beyond the tile. Then I will fetch this row. And again, I can keep reusing this, guys, right? So when I calculate this bottom half, right? Although they will potentially kick out early rows, but I don't care because I'm not using them anymore, right? So if you count this part in, now the total miss rate is even lower, only 1%, right? So that's how block algorithm works, right? So right now, and then I can move on, right? And I can keep calculating other tiles as before, right? As previous, right? And you might think, oh, well, they can kick out the upper portion. However, we don't care because we are not going to use it for a short period of time if we write our code and traverse the order of tiles correctly, right? So that sounds like a good idea. So it turns out this is the resulting algorithm we have, right? So this is the original triple nested loop, 3-level nested loop. And since we want to compute tile by tile, so we need to compute it by the dimension divided by tile sizes for each level. So that's why the outmost 3 levels, you structure it in this way. And the innermost 3, you are performing the matrix multiplications for each tile, each different tile you selected. So that's why here we do I++, JJ++, and KK++, and we set a boundary to be just the tile size. Okay. So now, after you revisit this algorithm, you might think, okay, most of the time, I'm just using only 10 blocks within the cache. I feel like I am not fully utilized the cache. So right now, I'm thinking, since I have 768 blocks, can I make my tile size large? So think about the case. If now the tile size is 32, what happens? All right, let's take a look. Okay, in the very beginning, discussion, a lot of you think it's A. So why don't you guys go ahead and discuss with your friend to see is it really A or something else? All right, let's take a look. Okay, after discussion, more of you think the answer is A. So can I have some of you sharing your thought with me? Okay, Hunter, do you want to volunteer? No, that's fine. Okay, Joshua.
Okay, so the tile size is 32.
The tile size is 32.
If 32 of our integers or doubles, or whatever they are, would be 4 blocks. 4 blocks.
4 blocks.
So then one tile, let's say our right matrix,
Mm-hmm.
will be 4 blocks by 32 blocks. So we're going to have a total of 128 blocks.
Okay.
That definitely fits in memory. We also have 32, so 4 more blocks that we have for the left matrix, and then for the output matrix, we have another block.
Mm-hmm.
So we're well under.
We are well under, right? So if that's the case, then that will be 384, right? And we have 768, so we are well under. That's what you think.
Yeah, I think we're well under, and I don't think we'd only get conflict misses at most once every iteration of one of the first 3 groups, and those happen a small percentage of the time.
Okay, so first of all, one thing we can identify is not this 2, right? Because we don't have capacity misses. We do have compulsory misses, right? Now, the only thing remaining, okay, again, a lot of cases, when we answer a question, we always forget. You tell people like, this must be that, but you don't provide proof it might not be others. How do you know there's no conflict misses?
That was very ad hoc. I haven't quite thought that through.
You haven't quite thought that through, right? So that's the blind spot when people are thinking about things. And it's okay if you are an undergrad student, but here you are at grade schools. So we definitely want you to put a reason why this is not the other. And in fact, if you do that kind of analysis, that will change your mind. How do you know if there is conflict misses or not? What? If we change the index or not. How do you know if we change the index or not?
It has to be greater than 64 to get into changing the next bit in the address.
Yes, but Is that sufficient enough for us to tell?
Yeah, I think so, because we know the tile size is 32, so we
Mm-hmm.
can give a rough estimate of what the addresses are.
Mm-hmm.
And 32 is,
That's only for the consecutive blocks, right? How about the ones that are not consecutive? How can you do that?
Are these stored? Is each matrix stored continuously in memory, or is it like the programming assignment where
Well, what I said in the very first slide. This is how it stores. That's the standard. Right? So, what's the next step now? What do you think the right next step would be? Remember what I told you. So this is, yesterday I have a lot of people in the office hour. People keep asking the same question again and again. Do I have to do cache simulations? Don't be lazy. We have to do a cache simulation here. I mean, you can definitely find some trick to identify that, but to be safe, let's do a cache simulation, right? Because a lot of people, they try to find tricks, they try to memorize this equation and that equation. Unfortunately, equations doesn't apply to all scenarios. A lot of people were asking, okay, is that the right equation for calculating the missed penalty? And I'm telling you, there is no equation for that. If today I change something, it will change. There's no equation for things. All the equation that you should know for this class, I have told you in the slides. If I didn't have an equation for that, that means that you should not find an equation for that, because there's really not one. And if you try to do one, I'm sure you would easily get lost in your midterm because you use that equation. So now, for this kind of question, if you are not confident, the best way is to do cache simulation. You know what the layout of a cache is, of a matrix in memory. So let's assume a starting address of your matrix, right? Even though it's not given, you can assume one. And no matter what you assume, you will always get a result mathematically. Really, this I can promise, right? The only thing that you know for sure, or the only thing that won't lie to you, is mathematics. If you don't know how to do it, you don't know how to do it, right? Mathematics is the most honest friend of you. So let's assume B00 start with this address, right? And if you have 2K matrices, and each element takes 8 bytes, then you can imagine the offset between one column to another would be 4,000 in hex. So you can easily say, well, if I assume like 20,000 is my starting address of B00, the next column will start with 24,000. And if you do the C equal to ABS, then you will figure out how to partition this address. And then you will figure out for those two, they will be mapped into the same index. And if you keep going on, what happened here? So the first column, everyone is at the same index. We only have 12 ways for this processor. Most processors has less than 16 ways. What does that mean? If you set your tile size to 32, you will see a lot of conflict misses when you access the next column. And the reason is because whenever I start fetching the 12th element in a column, I have to kick out the previous 12 blocks, one of the previous 12 blocks. And if you have 32, I'm 100% for sure the early ones are gone. Do you agree with that? And here, so far, we only use 32 blocks. And even though we count the other matrices as what Joshua said, we haven't used all the capacity. And we are going to see a lot of misses here. And every one of them is a conflict miss. So what's the majority type of misses here? It's going to be conflict misses. Right? So for this question, the answer is C. So what does that mean to you? What does that mean to you? Don't cheat during the midterm, because your neighbors are not trustworthy, right? Okay, so here's the problem, right? We have a lot of conflict misses. So how to avoid that? Since we have 12 ways, if we can stop somewhere before 12, then we will be fine, right? And if you want to find a 2 to the something that is smaller than 12, that's probably 8. Do you agree? So for now, let's say it's 8. So when we do tiling algorithm, a few things we have to take care. First, the tiling itself, if you set a good tile size that make your whole working set size smaller than your cache size, then you can reduce capacity misses. However, it doesn't change your data structure at all. So you might potentially have conflict misses. So if you want to avoid conflict misses, you have to change your tile size in a way that won't lead to conflict misses instead. Okay, so now we think A is the best size, right? So let's run the tile version of the matrix multiplication. Woohoo, demo time. Where's my cursor? Do you guys see it? No, okay, where's that? Oh, here we go. Okay, so let's run it. Okay, that was the previous result, if you could remember, right? So previously, it takes 24 for 2K, 24 seconds for 2K, right? Now, oops. Let me show this block matrix multiplication code that I have. It's exactly the same as what I show in the slide, right? Honest, no cheating. And let me recompile it. Okay. And let's see how it runs. So it would take a while. And I'm going to try many different block sizes. So in the very beginning, I'm going to try several different sizes. So you will see it's really improving compared against the baseline, which is the MM. And then I'm going to use various different block sizes to see if 8 is the best choice. So this is the set of demos that I'm going to run. And let's see how effective is blocking algorithm or tiling algorithm. Oh, why is it taking so long? Is it really running? Oh, wait. What is that? Hello? Okay, I'm confused. But it seems like this is the current runtime. So look at that. So previously, the upper part is the baseline. So as you can see, for the baseline, each of this, they have a cache miss rate that is around 20%, right? And no matter what size you're given, it's always 20%. However, if I change it to the block size that I want, like if I change to an 8x8 tile, right? As you can see here, the cache miss rate has significantly reduced, right? They are all at around like 0.01. One of them is 0.014. Have you seen that number before? It's it's very identical to our estimation, right? We said it's 0.0104, right? So our estimation is very correct, right? And what does that help our runtime? So previously, it was 23, but right now it's only 4. 6 times speed up. 6 times speed up. Did you see that? Okay. So now, you wonder, okay, here I'm using 8. Is 8 the best choice? So, let me run this. So, after we finish running the bottom parts, let's take a look. Okay, so this is the 2K 8x8. It takes 4 seconds. Is it the best? Is it the best? No. Which one is the best? 16. How about the miss rate? Whose miss rate is the best for 2K? 8. So first of all, in terms of miss rate, there is nothing wrong for 8x8. Look at the miss rate of 8x8. It's only 1%. However, if you look at the runtime, it's 4 seconds, and 16 is performing better because it only has 3.75. However, the miss rate is 7%. Right? So what does that tell you? Why? Why 16 by 16 is performing better here? Instruction count, right? So if you take careful attention to the data we got, first of all, we pick 8x8 as the tile size we want. And that's indeed correct because the miss rate is actually the lowest. However, in terms of the runtime, 16 is the best. And the reason is because if you check the instruction count, that actually makes significant difference. That actually makes significant difference. So some people, when you try to write a programming assignment, you're targeting at optimizing the cache miss rate. That's one of the right track. But cache miss rate, I think in the last lecture we also have the discussion. Cache miss rate only helps to improve your CPI. However, that's not everything, right? Because your performance is actually IC times CPI times CT. And the smaller the tile size. Question?
May take use of L2 or 3 much better than the S size. So does that make a difference other than the IC?
But do you think there's a big change in the CPI?
Oh, so the CPI could reflect sort of thing in the.
So the thing is that it doesn't make a difference, right? So what you mentioned is only if, okay, even though I have a 16 by 16 tile size, do they fit in L1?
Yeah.
They do fit in L1, right? And 8x8, because you don't have conflict misses, you don't even have to visit L2. So you already have the best memory performance. But what's wrong with 8x8? It's because you need additional iterations of the loop, right? So how many loop iterations you have to perform? If it's 8x8, right, you have to go to the outer loop every 8 elements. And each level, to judge if it's smaller or larger than the boundary, to perform an increment, everything counts. Everything counts. And after the midterm, when we talk about how this branch instruction, how expensive are they, you will figure out they are very, very expensive. Okay, but that's set it aside. Here, at least for now, you can conclude the reason why, even though 8 has the best cache miss rate, it doesn't give us the best performance. It's because at some point, when your miss rate is lower than a certain threshold, what really controls the performance is probably not the cache miss rate anymore, right? Remember MDOS law, right? Now, we lower the miss rate to a certain threshold. We can definitely make it lower, but maybe not that important anymore. So right now, the instruction count matters. And in fact, the instructions that make that are additional from tile size 16 to 8 are those control dependent instructions. And those are also expensive as well. So here, you have to remember our performance is a combination of 3 things. And there's definitely some kind of trade-off. There's no free lunch. There's definitely a trade-off between the tile size and the instruction count. Okay, but here at least we know a new technique called blocking and toweling. It's something that we can improve capacity misses, and if you tile size correctly, you are going to reduce conflict misses. And sometimes you might think, is there any way I can better utilize my cache size, but also avoid those control overhead by enlarging my tile size? So remember this, right? So one mechanism that I'm introducing here is matrix transpose. So the basic idea of matrix transpose is instead of I add one portion of the code as an overhead. So this, from here, I'm going to create a new matrix that is transposing the original matrix and put it in BT, B transpose. And now, because it's transposed, when I perform the matrix multiplication, instead of IIKK and KKJJ, I can now do JJKK. Right? So instead of traversing row and column, now we are traversing row and row. So what kind of misses do you think we can remove here? All right, let's take a look. Okay, so most of you think the answer is C, but why don't you discuss with your friend as what we have learned so far, right? All right, let's take a look. Okay, after discussion, more of you think the answer is C. So, can some of you share your thoughts with us? So if we don't change the tile size, we simply change the layout. Are we going to change the working set size?
No.
And also, are we suffer from capacity misses?
No.
Right? So capacity misses should not be in the picture. So it leads to compulsory misses and conflict misses. Do we still have to visit the same amount of blocks for the entire computation? Yes, right? So it's not compulsory misses for sure, right? So the only answer remains would be conflict misses. But before I said this, does this really reduce the amount of cache misses? How do you know?
The whole block is already going to be in the cache anyway.
Right. So a few things that you can do, right? You can definitely do a cache simulation. Or you can probably think about this, right? So if right now I transpose the matrices, right? And then every time when I perform a tile, for example, I still need to have the same amount of blocks if I make it like A by A, right? However, if I can transpose it, and potentially what happened is if I go to another tile, right? It was originally the lower tile, right? But right now, if I make it here, this is consecutive to the previous block, right? So instead of going an offset of 4,000, I'm going to an offset of 64, which is 40, right? So if you list the address, it gives you an advance to the index, not mapping to the same index. So originally the lower part, when the tile size is 32, it will kick out the previous ones. But right now, if they are transposed and arrange it to here, it's a different index. And if you do a calculation, right, if it's a 32 by 32 tile, each of them would be in 4 different indexes. So you will not be suffering from conflict misses anymore. But the compulsory misses remains. Agree? All good? Okay. So it means if we are transposing our data, we can potentially make our code go larger in one side of the tile, at least, right? So first of all, it will remove compulsory misses, right? And then if I can have it go through this way, I can potentially make it work out with a larger tile size. So let's take a look of how effective is matrix transpose position. So first of all, let me find a code of transpose. Okay, so the transpose is right here. And this is the transpose code. As you can see, instead of IIKK, I'm now doing JJKK. And let me do this. And let's run it and see what's going on. So again, I'm doing the matrix transpose with different sizes. And one thing I want to mention, the timer that I put here, they also include the transposition overhead. So it's not just the matrix multiplication itself, but also include the matrix transposition, to be honest, right? And let's see how much time it would take. Well, it take a while. It would take a while. Okay, it finished running the first set, and then it kept running with different tile size. Oh, okay, actually it finishes. So now, first of all, take a look of the runtime. So previously, the best we got for 2K is around 3.75. You remember that, right? Now, what do we got? Look, 3.9, 3.09 with 2K. Right? And with various tile sizes, we found it works really well at 2.6, at 64 by 64 with the runtime of 2.6. Although it doesn't give you the lowest miss rate, but it's low enough for the instruction count to be the majority of the performance issue. Right? So what that shows to us is that now, if we have transposition, at least right now, if you look at everyone, the miss rate is a lot. Well, so first of all, for the case of 16, the miss rate is actually a lot lower, right? For the instruction count doesn't differ. So the miss rate previously for something beyond 16, you will see a miss rate around 24. But now for 64, the miss rate is only around 2% because of the transposition, right? And another thing, why 64 is the best? Again, because of the instruction count is lower, right? So that's why when you use transposition, you are actually allowed to use larger tile size. But is this the best? Not yet. Not yet. So one thing that you can potentially do, right? If you look at the code, there is still one efficiency here. So again, memory instructions, they are potentially slower anyway. Remember what you learned from your assignment? Even an L1 access Even though it's a hit, how many cycles it would take? 5, around 5 cycles. What about other instructions? 1 or even lower, right? So if we could have avoid memory accesses, we should avoid. So the opportunity is actually here. If you look at CII and JJ, we don't change the CII and JJ that we would access unless we are out of the loop. Agree? So one thing we could do is we could create a variable here to store the temporary accumulation result. So we can eliminate that memory accesses. Some of you might be thinking, wait a moment, can the compiler do this? And the answer is, most of the time, no. Isn't that a surprise to you? That's why coding is so important. And this is not something the algorithm class would teach you. And this is actually not something the software engineering class would ask you to do. Because right now, it looks like, okay, I'm creating a new variable, make my code even more hard to understand. But let me show you how effective is this. So right now we were at around the performance around like 2 point something. Remember that? Right now, I'm doing this. Let me add. So this is the code that I have. So I did create a new variable here. And then let's take a look to see what was the result. What's the result going to be? So now I'm running it again with multiple different block size or tile size. And let's see. Okay, here's the result. Look, previously we were at 2 point something. But right now, what's the best? It's 1.87. It's 1.87. At tile size, 32. Right? So, one thing you will find is now we are best performing at 32. And 32. And another thing that you want to check, the instruction count. They all go from 6 something to now 4 something. A significant reduction. And some of you might be wondering, wait, the miss rate goes up, right? But you know, there's a lot of politicians try to cheat a lot of people, right? They would say, well, something goes up, so it's bad. But you should not only looking at just one number. Here, one thing goes down significantly, right? We only require almost like half of the memory accesses now. Because of what? We make that a register. Right? It's also another evidence that the compiler won't do that optimization for you unless the programmer declare that result as a variable. Okay, am I getting my voice back? Yes. Okay, so now, is that the best? A question?
For the previous slide. So I was looking at the data, and for the 32 case, it has a greater instruction count, a higher miss rate. and more accesses, yet it's faster than the 64 keys.
Uh-huh.
And I was wondering if all those properties, why is it still faster?
Which one is faster?
Thank you.
Yeah, the CPI of that for 32 is lower for a variety of reasons. And part of the things that we didn't talk about here is in memory accesses, we do have, if you are consecutive, that's another reason why when you transpose it, it will be a lot faster because we have vector instructions. And when you turn on a fully optimized compiler, they will automatically leverage that vector instruction. So at a size of 32, it works better. Okay? So, the last thing. Are we done our best? Not yet, right? So one thing that we were observing is, okay, if the tile has a vertical dimension that's surpassing the number of ways, we are still going to see conflict misses. So if I want to further make my cache miss rate going down, the best practice would probably be I should have a rectangular tile where the horizontal, which goes to different indexes, should try to utilize all the sets I have. But vertically, this should be aligned with the number of ways that I have. Right? So a rectangular one is probably the best. So now I'm going to change my code again with different tile sizes at different dimensions. So here's the code. So it's rectangular plus transposition, right? So right now you see I have two different tile sizes, X and Y. And I only increment the X in the innermost loop. So that means that horizontally, I'm going to go from different size than the vertical size. So ideally, and the first argument here is the horizontal, and the second argument here is the vertical. And now I'm going to run them and show you what the performance looks like. Okay, so here's the result. So I run several different sizes, A by A, right, with the register optimization and transposition is around 2.25. 8 by 16, as you can imagine, because we have more ways that we need for a set. So apparently, the miss rate is a lot higher. And you can see the number of cache misses goes up. So the execution time also goes up. So you know, if I have a rectangular, which is vertically thinner, that's not a good idea, right? So we want a rectangular that goes horizontally, right? So if I do it 16 by 8, woohoo, right? The execution time is 2.21. But that doesn't utilize all my capacity, right? So now I go a little bit more aggressive, 32 by 8. The execution time is right now only 1.82. And some of you might be thinking, can I be a little bit more aggressive? So I do 32 by 16. And then you see those conflict misses goes back. Right? So my execution time goes up again. So if you check all the data, right now you can recognize what's the best size? It's now 32 times 8. Right? And why the second argument is 8? Because we only have 12-way associativity. If you make it 8, that will fit into the set better. Why the horizontal is 32? Because that's the best size that wouldn't go over the capacity. Right? Question? 32 is the set. And 8 is the way.
So it's like this
this way. Okay, horizontally, right, as I mentioned. Okay? Question?
So how would you take care of the case where like your rectangular doesn't perfectly match to your square matrices?
So if that's the case, right, you have to add additional conditions in your loop, which would add some overhead. But for the simplicity of the class demo, so first of all, for this code, if you run it on a size of matrix that's not 2 to the something, it will seg fault for sure, because we don't have those condition checks. So if you want to add everything back, that will give you probably around like 5 to 10% overhead. Okay, but you have to do that in your assignment and other places as well, right? If you want this code to be solid and performing, like in production. Okay, so, and also if you look at that, right, the miss rate of 32 by 8 is already very, very low compared against the previous version. So that's why 32 is now a better version. 32 by 8 is a better version compared against 32 by 32. Because we have good enough instruction count. We have low enough cache miss rate. Okay, so takeaway here is we do have a lot of software optimizations that you can explore. And matrix transposition is changing the data layout. So changing the data layout sometimes is very effective. And this is the case where we use the change of data layout to avoid conflict misses. And sometimes, if you can reduce memory accesses, you should try, right? So for example, if this could be a local variable, and if you don't have a lot of local variables in your code, remember you have 16 registers in total that the compiler may be able to use. Try to make it a variable so that the compiler might be able to do something. Okay, so now let's talk a little bit about other approaches. So far we only talk about hardware-only approach and software-only approach. How about hardware-software co-design? So by hardware-software co-design is the hardware provides some kind of additional support and the software can use. And software controls the use of it. So for example, we talk about prefetching. And we are so struggling with the prefetching can only work if you have good spatial locality. However, if from the software programmer's perspective, this is something the software can predict. So turns out there is a prefetching instruction that people can use. And in x86, it's called mmprefetch. And here I'm going to show you a demo using mmprefetch to even make transposition faster. So this is a highly optimized code of transposition. And here I'm adding mmprefetch instruction by giving it a hint, which is basically an offset from the current address. And let's see how effective is that. So without prefetching, it takes 0.4 seconds to perform the matrix transposition. Right? So you know that the matrix transposition is actually not that slow. But if we could have an optimized prefetching, okay, it doesn't work for this one, right? So for this particular processor, it tells you how good its prefetching unit is, right? Because with prefetching, the software programmer think, okay, we are doing a good job. But apparently, you're adding overheads, right? So this one doesn't work. However, today, if I change my processor, so saying that if I have a processor, okay, so here it's an, okay, let me do it again. So here it's a processor by AMD. Oh, wait, why is it without prefetching? Oh, okay, so this is, no, this is Ninetales. So this okay, here we go. So this is a processor by AMD. With prefetching, Without prefetching is also about 0.4. With prefetching is actually 0.3. So what does that mean to you? This is something related to the hardware. If you have a hardware that already does good prefetching, then it doesn't help. However, if you find prefetching works for your processor, first of all, congratulations. You find a way to accelerate your program. Second, this processor doesn't have good prefetcher. Okay, so, but it also means that this is a hardware-dependent software optimization. And another one, which you read a paper called scratchpad memory. And I don't want to dive into the detail of the paper, but the high-level concept is that so far, when we talk about caching, we always let the hardware decide what to keep in the cache. So for example, for the cases of conflict misses, if I could have declared at least keep one of the data structures that I think that matters instead of keep everything like doing the LRU forever, that would change things. So the idea of scratchpad memory is actually that a software programmer controls what to put inside the cache. And there is another potential benefit of using scratchpad memory because we exactly know what you have in a cache. So we don't need a tag array. So what happens is that whenever you want to put one of these pieces of code, the processor would actively fetch the range of data that you want, put them into the scratchpad memory. And the programmer's memory controller would know, for this range of addresses, we should automatically go into the scratchpad memory and access the corresponding offset. So in this way, you don't actually need a tag. And the programming interface could be made simple. So one of the architecture that implements the scratchpad memory idea is actually the GPU architecture. So in NVIDIA, they have a shared memory. So the shared memory, I personally think is a wrong term because it doesn't really share with others. It's only visible to the same string multiprocessor. So it's actually an exclusive cache to that string multiprocessor. It's not shared at all. So the wording is actually not correct. And the shared memory is indeed an implementation of scratchpad memory. So to use that, all you need to do is that you add a decorative in front of the data structure, typically an array. And then you said this should be in a shared memory. So whenever I launch this kernel function, this array will reside in a scratchpad memory. So when a memory controller sees you want to access an address that falls into that range, instead of going to the cache, I will go into the scratchpad memory. And during the scope of this function, this content is guaranteed to be within the scratchpad memory as long as the data structure fits into the size. So that's another way of managing cache efficiently. So far, here's the summary. We have learned a lot of mechanisms to optimize cache performance. But remember, all of them has their pros and cons. So now let's talk something really quick. So, there are always cases that we can avoid a miss. Like, I don't know how many of you watch baseball. I like playing baseball. And in my team, I sometimes be the pitcher. I'm the pitcher. And, sometimes there are people on the base, especially when people reach the third base. What I'm thinking is what I'm thinking is actually not, how can I avoid miss a point? Is how can I minimize the points that I miss? Because that miss is happening, right? So if there are cases that we are going to miss anyway, how can we handle them better? So first of all, part of the miss penalty coming from the fact that we have limited bandwidth. So when we handle a miss, for example, especially one of the problematic things that make miss especially problematic is, what if I evicted a block that is dirty and I have to write it back? So what happened now is that before I can fetch a new block, I have to serve this write back first. And because you have limited bandwidth, typically like a 128 or 64-bit. So if you have a block with 64 byte, you might need to partition these transactions into 8 different times, right? So here I'm only, because the slide is not that long, so I only show it for 4, right? So after this 4 writes, you can finally fetch the block and return it to the upper level memory hierarchy. So that's actually not very efficient. So there are several optimizations that the hardware can do without letting the programmer know. So for example, the first thought is that, what if I'm only accessing the first word in a block? Right? The previous mechanism, you have to wait for the whole block arrive before you can do anything. So right now, I'm just returning it whenever the data I want is already there, without waiting for the whole block to be presented. And is it the best? Now, the problem is this, right? The write seems to take a long time, right? It's almost like another miss. So how can we avoid the overhead of writes? So if you have taken operating system class before, Butler Lamberson, he has a good paper regarding end-to-end system design. And he was talking about, if you can put buffer, do it. So same thing here is that we create a write buffer in between L1 and L2. Whenever we have to write back, instead of writing it directly to the next level, let's write to the buffer first, right? So write to the buffer, which is fast, and then we can fetch the block. That's how we, and then you can still apply this critical word first. Okay. So now, sometimes if you're unlucky that you keep modifying the same block again and again because you have conflict misses, how can we make it more efficient? So you might think, whatever in the buffer, I should write it immediately, right? But if you keep it longer in your buffer, you can potentially merge the data you want to modify in a block together, right? So in this way, you can avoid the penalty of consistently writing. All right, so that concludes our discussion in memory cache optimizations, both hardware, software, and also a case study. And before you leave the classroom, a few things. First of all, we have assignment 2 due tonight, and we have reading quiz 5 due next Tuesday, assignment 3 due next Thursday, programming assignment 2 due after the midterm, and there's a midterm in person only, closed book, closed, no laptop, no mobile phones. You can use a calculator, but only use your own. So if you still have time to order it on Amazon, right? And we will release a sample midterm question together with the slides on next Thursday. All right? Other than that, enjoy the rest of your day. I will see you next week.